All right, we're talking about 7.4 again in Calculus 30. And what this is using the derivatives of trigonometric functions. And we're combining this with the concept of related rates. So this example from this section talks about is really the applications of trig functions, trig derivatives, and related rates all mixed up together. So this is our first real example here from the textbook where we're going to use trig and related rates together. So if we read through this problem here, it says this: two sides of a triangle have lengths 15 and 20 meters. So that's two sides of a triangle. The angle between them is increasing at pi over 90 radians per second. Okay, we could stop right there and we could identify a couple things. First of all, this is a rate of change, right? So if we're talking about related rates, we're talking about a rate of change here, and this is of the angle, okay, between this length of the triangle and this length of the triangle. The question is, how fast is the length of the third side of the triangle changing? So there's another rate, okay? The third side is changing when the angle between the sides is pi over 3. So let's just take a look at our drawing here. Let's put the triangle up there, and here's the angle in between the two sides, and their lengths 15 and 20. The third side, let's just make it some random variable because it's going to change, and we don't know what it is right now. And so let's just make it x. So what we have to understand in the question is that this question is given us the rate of change of an angle. So this angle we've said is theta. So the rate of change is the derivative, right? The instantaneous rate of change, and that's going to be pi over 90 radians per second. So that's the given rate of change. And in a related rates problem, there's another rate that we're trying to find. And so the question says, how fast, so here's your indication for a rate, is the length of the third side changing? We said that that is x. So we're looking for x prime. That's what we don't know. So these rates are related, and we're going to just finish off what's given here. The point in time that we're looking is at the point in time when this angle, theta, is pi over 3. So we're going to say at theta equaling pi over 3. So again, this is the instant. It's not a time, it's not seconds or minutes, but when the triangle is has an angle of pi over 3 between these sides, that's at the snapshot in time when we want to know how x is changing. Okay? So in a related rates problem, look for a given rate, look for an unknown rate, and look for some point at which you want to, calculate this rate. And this is the sort of constraint. You might hear it said. It's a constraint. Okay? So this is the point at which we want to calculate this change. Because, face it, as this is changing, and it could be changing at this rate the whole time through the question. So this is changing at different rates every instant. And so what instant are we talking about? The instant when this happens. Okay, so we've identified what we're given, what we want to find, drawn a diagram. And so now what we have to do is, often the tricky part, is try and find a relationship between everything here. The 15, the 20, the theta, the x. How do we connect all this together? And specifically, how do we connect these two things? The two related rates, and how are they related? So we want to identify that. And now, it may not be very obvious. You may think, oh, I know, trig functions. Hang on there. This is not a right triangle. At least it doesn't say it's a right triangle. And we can't assume that. But it is a triangle. So you can use something that you've learned before in math called the law, the cosine law. And you may not remember the cosine law, but if you thought of the cosine law before I mentioned it, kudos to you. Now the cosine law is written like this: x squared, and that's the side, the unknown side, and here is the angle that's opposite, right? So the x squared goes on this side, and the cos theta goes at the very end. Right? That's how you can remember it. It's the side squared on one side of the equation, and then the cos theta is in the very end. What happens in between? Well, you've got 15 squared plus 20 squared. It's a lot like Pythagoras' theorem. It kind of looks like a lot like Pythagoras' theorem. But because this isn't a right triangle, you have to account for the fact that this is not a right triangle. And so that's where all this other stuff comes in. So 15 squared plus 20 squared, and then it's minus 2 times 15 times 20 times cos of theta. All right? So that's the cosine law, and this is the equation that we're going to use to connect all this stuff. So let's simplify this. X squared, this is 225, that's 400, so that's 625. 2 times 20 is 40, times 15 is 600. Cos theta. All right, so we've got this a little simplified now. Remember, we do not have to solve for x, okay? And why do you don't have to solve for x? Because in related rates problems, we are differentiating with respect to time, okay? So we don't have to worry about which one is our preferred variable, right? Are we doing dx, dy dx? Are we doing dy d theta? No, we're not doing either. We're differentiating both dx with respect to time and the theta with respect to time. So that's another common thing with these related rates. We differentiate everything with respect to time. And so because there's no preferred variable, we're going to have a theta prime in our differentiated equation and a x prime in our differentiated equation, because t is our preferred variable, which doesn't show up anyway. Right? So we differentiate this. What's that? Well, 2x times x prime. Chain rule, right? 2 power rule and then chain rule. This is 0. This is minus 600 because the constant, so we'll just leave it out there. And what's the derivative of cos theta? Well, derivative of cos we just learned was negative sine theta. And then chain rule says we have to find the derivative of this, which is theta prime. Okay? So that is mondo important right there. Super huge. Okay? To differentiate that. Pretty exciting. Good job. If you did that, if you understand that, okay? So now what we want to do, you don't have to simplify. I would suggest doing a little simplification. We've got two negatives multiplied here, right? We got a 0, whatever. Let's clean this up a bit. 2x, x prime, do that. And let's just make this positive 600 sine theta, theta prime. All right, so once we've got that cleaned up, now what we want to do is we want to find out this right here, right? So let's divide both sides by 2x to solve for x prime, because that, remember, that was in the question. Here we go. That's what we're looking for. See? So we solve for x prime. What do we get? 300 sine theta, theta prime over x. Now, a couple things we want to pay attention to, I guess, here. This is what I'm trying to find. Awesome. This I'm given. Good. And theta, look up here. Theta, I'm given. Good. One small problem is, yeah, right. I don't know what x is. And in order to evaluate this x prime, I need all three of these things. I need to know what x is. So don't be alarmed. Don't be alarmed. You think to yourself, is there a way that I can figure out x at the point in time that we're talking about here? So the point in time is when theta is pi over 3. So if you look at this and you say, okay, 15 is given, 20 is given, when this is pi over 3, could I calculate what x is at the same time? Yeah, you could. You just simply put, look at this, pi over 3 right here, and then you can solve for x. So that's what we're going to do now. And you just basically take this, put in pi over 3 right here, or down here. This is the simplified version. Put pi over 3 there, and we'll solve. So let's do that. Let's do that real quick. So there's the equation with pi over 3 in it. How do we know what cos of pi over 3 is? Oh, whoops. Yeah, no, that's good. I'm still just solving for x here. This is just a little bit of an aside. I'm not doing this yet. Okay, this is just a little bit of an aside here. So let's solve for x. Cos of pi over 3, if you think back to your unit circle really quickly, pi over 3 is 60 degrees here, right here. And so this would be the first coordinate would be 1/2. Okay, so cos pi over 3, right, should be 1/2. So that's x squared equals 625 minus 600 times cos pi over 3 is 1/2. X squared, 625 minus 300. X squared is 325. X is the root square root of 325. Okay, so there you go. That's don't bother simplifying it right now. Just leave it like right there. And now that's our x value that goes where? This x value goes now into this differentiated expression, and we can solve for x prime. So now we have everything we need. Let's do that. All right, so here I filled in all the values right here. And of course, the theta is pi over 3. The rate of change, right, which is the theta prime here, the rate of change of theta is pi over 90. That was given in the question. And this root 325 is what we calculated x to be at that point. So you can just plug all this into your calculator and get a decimal answer. It's totally fine. You don't have to have an exact answer all the time. I don't know. Preferably it would be nice to do, but at this point, if you get this right here, that's great. Okay, just right there, that's great. I will simplify this maybe in a second here, but you should get something approximately close to 0.5. All right, and that's what it is. So it's 0.5 as a decimal here, not exact value, but 0.5 what? Well, let's look back to the question. The angle is changing at radians per second. Would that make sense for x? No. X is not measured in radians. X would be measured in, look at that, meters. X is going to be in meters because these are in meters. And of course, the time we're talking about is per second. So x will be changing at 0.5 meters per second. Okay, you might want to write that out in words, depending on what your teacher wants. The rate of change of the third side of the triangle is approximately 0.5 meters per second. So if that's good for an answer, great. I'll show you just quickly on the side here. I'll just do it on the side and show you how you would simplify this to give an exact answer. Okay, so here on the side here, this is how you would work this out to give an exact answer, which is, ideal, right? In calculus, exact answers with radicals are ideal. So just one thing here that you want to make sure you are aware of, that sine of pi over 3 is root 3 over 2. And you can just get that from the unit circle. You should have that unit circle memorized, at least the first quadrant right here, okay? You should probably have this memorized, or at least handy. You get a cue card for your test, you can use that there, whatever, but you should have that memorized, really. And so with that, then you can simplify here, radicals, this last step here, multiply top and bottom by root 13. Because technically, in the denominator, you shouldn't have a radical in the denominator. That's technically simple form, but decimal, and simple form right here is your answers. Okay, so that's a problem there. Pretty classic, pretty straightforward. The only thing that's not straightforward is this cosine law component. You won't see that a whole lot, but the basic format of this type of question would be the same for related rates questions in grade 12 calculus, 30 and AP. And first year university related rates problems. This is the basic stuff. If you know how to do this question, you're in really good shape. Okay? So there you go. Hope you learned something today. And hope calculus goes well.